This is lecture video 54, and we will cover tests for convergence and divergence in this lecture video. In particular, I will explain how to use direct comparison test. So look at this first example, please. Here we want to deal with this integral. And okay, at first sight, we understand that it's an improper integral of type 1 because of this interval of integration is infinite. So this is a type 1 improper integral. Remember, type 1 means interval is infinite. We also covered integral of type 2. And it is related to which situation? In this type, the function inside the integral has discontinuity. So is this continuous? If this continuous f of x appears inside the integral, it is type 2. So how to deal with improper integrals of type 1? So you just name this part as some variable b, and then you need to send b to infinity by taking a limit. After doing this integral, you need to put here a limit operation as b goes to infinity. But the problem here is about the difficulty of the evaluation of the integration. So this is an integral that we cannot evaluate it by hand. It is not an elementary integral. We cannot evaluate this integral by hand, meaning that this is not an elementary integration. So it is not possible for deciding whether this integral is infinite or finite by using the standard computation. But you know, we don't want to compute its actual value. We just want to determine whether it is convergent or divergent, meaning that whether the result is either finite or infinite. So to decide this, we have a very useful tool, which is called direct comparison test. Okay, let's try to understand this test. So if you have an ordering between your functions, I mean, if you know such an ordering between f of x and g of x, then it is possible to comment on the convergence and divergence of them. They are related somehow. So let me state it with you here again. So the direct comparison test. How it works? First of all, you need to have such an ordering between your functions, and your functions should be positive functions, non-negative functions. So the first statement goes like, if this integral from some arbitrary real number a to infinity of g of x dx converges, this means that the result of this integration is a finite number. Then if the integral of the bigger terms are finite, then you can easily conclude that the integral with the smaller terms will also be finite automatically, right? This also converges. And similarly, second statement, if the integral with the smaller terms with f of x diverges, meaning that if the result of this integral with the smaller terms gets already infinite, then the integral with the bigger terms with g of x will automatically be infinite, right? Also diverge. So these are the two conclusions of the direct comparison test. Let's try to apply them in these examples. So first example. By the way, we also have this remark here. Let's call it as a remark, saying that we stated direct comparison test for the improper integral of type 1, you see. It is also valid for the improper integral of type 2. Okay, so let's apply direct comparison test in the next example. By the way, before moving on to the next example, let's complete the example that we started in the beginning of this lecture. So we were dealing with this one. Okay, let's create some space here. So we were trying to understand whether this improper integral of type 1 converts or diverts. This is the question. We don't want to find the exact value of it. We just want to understand whether the result is finite or infinite. Okay, so now we need to search for a way to relate this function with a bigger or smaller function. We need to find such orderings. Okay, so let's start comparing with this inequality. Okay, obviously, if x is between 1 and infinite, x is less than x squared, right? So if you multiply each side by -1, so minus x squared, so the inequality between should be reversed, right? So like that. Okay, let's also put this equality sign because x can be 1. Okay, I reverse the inequality. Next, if I put this values minus x or minus x squared to the power of exponential function, then this inequality should be preserved, right? Okay, so you know this is our g of x and this is our f of x now to be used in the direct comparison test. So this is the original function that we want to understand. Now I relate it with a bigger function. Now I will try to understand whether this improper integral with the bigger terms are convergent or not. And this is something that I can handle. Now you see, instead of x squared, we have x, and it is easier to integrate. We can evaluate it by hand. How we can evaluate it? Of course, we will be writing b here. We will evaluate the integral, and then we will send b to infinity. So let's deal with this integral and then limit. So how to integrate e to the power minus x? It is itself divided by -1. That's why I put an extra -1 here. Okay, let's recall it. Integral of e to the power k x dx is itself divided by this constant k. Okay, so then you need to insert the upper lower boundaries like that. Okay, then what we have? Limit b goes to infinity, insert b first. E to the power minus b minus plus, insert 1. Okay, then I need to send b to infinity. Let's write this as a quotient, like 1 over e to the power b, 1 over e. Okay, if b goes to infinity, this part goes to infinity, 1 over infinite is 0, right? So that the result of this improper integral is in fact 1 over e, right? So the result is finite, as this finite number 1 over e. So this is a finite value, meaning that the improper integral that we start with, which is the integral of the g of x function, 1 to infinity g of x dx, we computed it here, from 1 to infinity e to the power x minus x. Since the result is finite, it is convergent, it converts. Okay, now it is time to use direct comparison theorem, direct comparison test. So if the integral with the bigger terms converts, then the integral with the smaller term will automatically converge, will automatically be finite, right? So the conclusion line is, then the integral with the smaller terms, I know that f of x is smaller, you see, is also convergent, let's say just also converge by direct comparison test, okay? This is the problem that we start with. Okay, that's how you use direct comparison test. Let's move on with the next example now. Okay, so let's try to find an upper or lower bound for this original f of x here. So it's you can use sine square is between 0 and 1, right? And then if I multiply every side with 1 over x squared, what do I obtain? 0 sine square x over x squared and 1 over x squared. Okay, so this is an upper bound for the function that we are dealing with. Now, I want to understand the result of the integral with these bigger terms. And you can easily recognize it as a p series, okay, as a p integral. So we recall in one of the previous lectures, we understand this type of improper integrals. X to the power p from 1 to infinity. So the result of this improper integral depends on the number p. If p is greater than 1, it converts. And if p is less than or equal to 1, it diverts. Okay, so this is called as the p-test, and you can use it in your solutions. So let's see, what is p here? P is 2, which is bigger than 1, so we are in this case, right? That's why this improper integral is improper integral converts by this p-test, by p-test given here as p equals 2 is bigger than 1, it converts by p-test. If the improper integral with the bigger terms converts, then the improper integral with the smaller term will automatically converge by direct comparison test. Then you can conclude that the improper integral from 1 to infinity with the smaller terms also converts by direct comparison test. So we are applying the result of the direct comparison test here. Okay, let's move on with this example here. So similarly, we will try to find an upper or lower bound for this function. So let's first try to understand this expression without the square root. So look at these two quotients, which one is bigger? So here the denominator is obviously smaller than the denominator here. Smaller denominator means bigger quotient, right? Like that. And then you can put your square roots without reversing the inequality, right? So what is this then? What we have on the right hand side? It is absolute sine of x, and x differs from 1 to infinity, which is a positive real value, so it is just 1 over x. Okay, let's try to understand the behavior of this part inside the improper integral like that, dx. So you should recognize this as a p-test immediately. Here p is 1. Okay, it is in this form, right? X to the power p, where p is 1. So we are in this case now. So it diverges by p-test, then automatically the improper integral with the bigger terms will also diverge by direct comparison test. Also diverges by direct comparison test. If the smaller integral with the smaller terms is a divergent one, integral with the bigger terms will obviously automatically be divergent. Like that. Okay, so let's move on. In this example, it is very similar, but this time it is not an improper integral of type 1, but type 2, because the interval of the integration is not infinite, but the problem is about the denominator of the function. Here your function is what? It is cosine x square root of x, which is discontinuous at which point? At x equals 0 point, which is this lower bound for the integral. So it is because of this discontinuity, this is an improper integral of type 2. And For type 2, we have a similar result like p-test. This is for type 1. This is an improper integral of type 1. So let's write a similar result for the improper integral of type 2. So we want to understand, this time the interval is finite from 0 to 1. Here you see it is from 1 to infinity. The structure is the same, and the convergence or divergence behavior of this improper integral of type 2. This is a type 2 integral because your function has a discontinuity point. This is discontinuous at x equals 0, so it is of type 2. So the convergence divergence behavior of this type 2 integral totally depends on the number p. And you kind of exchange these two sentences. This time when if p is greater than or equal to 1, it will diverge. And if p is less than 1, it will converge. Just like the reverse of this result. Okay, so now let's try to use it for this example. How can you find an upper bound for cosine x, for example? Cosine x over square root of x. The upper bound for cosine x is obviously 1. Okay, now let's try to understand the behavior of this function over this interval. But as as we deal with, as we are going to use this p-test, let's just put here 1, okay? And then we will see that it will be a convergent one. That's why you can just add some more interval to your integration. Okay, cosine x over square root of x dx. Sorry, we were dealing with the upper bound, so it is just 1 in the denominator. What is p here? P is 1 over 2. And this is an improper integral of type 2. For type 2, we have this p-test. For type 2, okay? Like that. So p is 1 over 2. It is less than 1, so this means that the improper integral converges. Then, as the improper integral with the bigger terms converges, then you can directly conclude that the improper integral with the smaller terms will also be convergent, okay? 0 to 1 dx also converts. And then you can easily add some more interval to your integration because, this continuity point is away from the interval from 1 to pi over 2. So you will just add some finite value to your integral. So you see, I can safely extend the interval of integration like this. It will still be finite because I am just adding a finite value to the integral that we have found, which is convergent in the previous step. Also converts, okay? So from 1 to pi over 2, you can safely pass. Okay, so last example for this video is this one. We want to understand whether this is a convergent or divergent integral. First of all, just note that it is an improper integral of type 1 because the interval is infinite. Okay, then we will try to find an upper or lower bound for this integral, right? But we have this. And okay, what do we have here? If you do this product, you obtain square root of x plus x to the power 3 over 2. Let's write this square root also as a power function, 1 over 2. Okay, we have this type of function. And if you compare it with this one, what do you think? Which one is bigger? As you have a bigger denominator here, you will have a smaller quotient. So I should put this inequality in the middle. Then you can start analyzing the convergence behavior of this function here, which is the bigger one. And notice that it is a it is in the P series form where P is 3/2, which is bigger than 1. As it is bigger than 1, this improper integral converges. That's why, by using direct comparison test, since the integral with the bigger terms is convergent, automatically the integral with the smaller terms will also converge by direct comparison test, right? Also converges by direct comparison test. So I stop here for this lecture video.